all of you to this session of heat transfer. In the previous lecture, we had seen how the one-dimensional steady-state conduction equation can be applied to the cylindrical surfaces when thermal energy generation is considered. Today we'll see the same thing, but the geometry of the surfaces would change from cylindrical to spherical. So let us see how we can start with these spherical surfaces. So in this lecture you would be able to understand the one-dimensional steady-state equation with thermal energy generation for spherical surfaces. Let me tell you that you will find that this is somehow similar to what we did for the cylindrical surfaces. There is very little change in the process in the deduction process which we had done for the cylindrical surfaces, and primarily you will find that the objectives and the lecture outcomes would be also same for cylindrical surfaces as well as so you will be able to investigate the temperature distribution. That means you will understand the sharp differences between the temperature distribution for plane walls, for cylinders, and for spheres. You will understand how the temperature distribution, the formulation of temperature distribution, how does it change according to the change of geometry. That would be exposed to you through this lecture. Now, I hope that you will be able to understand the one-dimensional steady-state heat conduction with thermal energy generation for spherical surfaces. You will be able to analyze mathematically the temperature distribution. That was what we are talking about. You will be able to find out the mathematical modeling of temperature distribution, and you will be able to calculate the heat transfer rate for the different geometric surfaces like plane walls, like cylinders, and like spheres. The first of the two, the later of the two, we have already done through our last two lectures, and this is the last one. So with this will be with this lecture we'll be closing the one-dimensional steady-state conduction equation for various geometric surfaces. Okay, so let us move on. I think all of you have gone through these outcomes, and so after this discussion let us move on to the derivation of the one-dimensional steady-state conduction equation for spherical surfaces with the consideration of thermal energy generation. So let us start with that. Okay, so let us consider a sphere, a solid sphere, which has a radius of r0, is transferring heat because of the internal heat generation or the internal thermal energy generation Qg. Qg is a volumetric heat generation, so that the surface of the sphere is maintained at a temperature Ts, and you know the sphere is placed at a certain surroundings whose temperature is T infinite. So the question is, how do you conceptualize or mathematically address this heat transfer? What is the mathematical formulation of this practical problem? So from the basic understanding of the one-dimensional steady-state conduction equation, we can write this basic formula here. Now this this is because of the heat transfer, and this is because of the heat generation or the thermal energy generation. And since we have assumed that the heat transfer is taking place under a steady state, so that it means that no energy will be accumulated after the steady state has passed. Okay, so according to the principle of steady state, the properties remain invariant, so there will be no energy accumulation within the system. Okay, so now the question is, how do you define this QR? This QR is nothing but the heat flux. We had already told while describing the equation for cylindrical surfaces. So now let us move on to the formulation of this thing. So I'm very sorry that I have written okay, that's all right. So QR is a heat flux, so you can write ddr of Now always remember that why we have only considered this part only, because heat transfer is taking place only in the single direction. The other two direction has not been concerned here. So this is the heat transfer in the single direction in the one dimension, and this is the internal thermal energy generation. Okay, so now you know what is kr. So this is k dt dr. So we are writing the Fourier's law. According to Fourier's law, the temperature gradient is written here, and this is the material property, thermal conductivity. And you must know that 4 pi r square, or okay, we will use general r square. That means we are considering a strip over here, over the sphere, which has a radius of r, and we are doing this calculation for that certain strip. Okay, I haven't drawn it, but you can understand it. So let us consider a strip over here. That means this is our dr thickness, and it is at the radius of r. Okay, so now, and again it would be 4 pi 4 pi r square into qg, that is equal to 0. Okay, so this is our simple equation. Now the term which is varying here is this r. Okay, that means we can simply deduct this 4 pi part from both the equations. We can simply remove this from both the equations, so that it will remain like this, right? And you know, we have assumed a constant thermal conductivity material. That means we have considered an isotropic material, so the thermal conductivity doesn't change. So this thermal conductivity can be treated as a constant. So dividing this equation by the thermal conductivity, we are left with this. That means we can now simply rewrite this equation in this format as ddr of r square dt dr plus r square qg by k equal to 0. Now just little bit of rearrangement, simply just rearranging the equation, we will find that this becomes minus of qg by k into r square. That is very simple. Now we would like to integrate the equation. After integration, after the first integration, what will happen? I am not going detailed, I'm not going into the detailed calculations, because that would take much time here. So it will be r cube by 3 plus c1, right? c1 is our first integrating constant. So r square dt dr becomes equal to minus r cube by 3 into qg by k plus c1. So this is our first understanding after the integration. Now here we can see that this is our function here, and now if we divide this equation by r square, what will happen? There will be no r square here, and this r cube would change into r, right? Very simple. And there will be a r square present here. Now again we can rearrange this equation, dt, which is equal to into dr. Very simple. Now let us integrate it. Let us integrate the equation again. So what will happen now? Very simple. It will be equal to t, and this one will be equal to minus r square. Okay, I would like to write in this format, minus q g by 6k into r square. I believe that you are understanding why this 6k has been formed, or how this 6k has been found. That is r integrating r, it becomes r square by 2. So 3 into 2, 6. Okay, very simple. And this one would be c1 by r, right? Basic integration, and you will find a term which we call as c2. Now again, we'll be trying to define this equation. We'll be trying to define this equation by the help of the boundary conditions which are available to us. Okay, the basic boundary condition, that means at the very simple boundary condition which is easily identifiable, is that at r equal to r0, that means when the radius is r0, the surface temperature of the sphere is maintained at Ts. So you can simply write at r equal to r0, T is equal to Ts. I hope you are getting this thing as the bracket, the comma. Still I will rewrite it once again. So at r equal to r0, T is equal to Ts. Now coming to the second boundary condition, which would help us to find out this formulation. Okay, now how we can find it? This will be very simple. Look, the problems which we have treated till now, they are all symmetric problems, and since here there is only radial heat generation and the heat transfer is taking place in a steady state in one dimension only, this problem should be also of symmetric type. That means at the center, that means at r equal to 0, at the center point, the temperature gradient dt dr would be simply 0. Okay, so at r equal to 0, temperature would be dt dr would be 0. Now implying this second boundary condition, we can find that the c1 would turn into 0. Okay, this is very easily identifiable, that c1 would turn into 0. Okay, so no need of calculating this dt dr. We can simply understand that at r equal to r0, this Ts would be equal to minus qg by 6k into r0 square. Okay, r0 square plus c2. So with this understanding and a little bit of rearrangement, so after rearrangement we can write, or we can easily understand, that Ts plus qg by 6k into r0 square would be equal to c2. So after this understanding, we can simply generate the temperature distribution formulation as T is equal to Ts plus qg by 6k. I am doing in a single step here, please concentrate. It will be 1 minus r square by r0 square. Okay, that is the point I am trying to make here. So it would be like this. So this is our temperature distribution. So when the radius, so the radius of this sphere is r0. Okay, and if you want to know the temperature at a certain radius r, then you just need to put the value of this r, and if you know the surface temperature, then you can calculate the temperature at any radius. So this is our temperature distribution. Now the question is how you can find the maximum temperature. Now here we have already defined that at r equal to 0, that means at the center of the sphere, dt dr is 0. So that means the maximum temperature, the minimum temperature would lie here. Now the question is it maximum or minimum? You will find that if you go on calculating the derivations, you will find that this dt dr would turn to 0, and this second order derivative, that means d2t dr2 would be negative. That will indicate at r equal to 0, that means at the center point of the sphere the temperature would be simply maximum. So let us define this, let us consider this maximum temperature as T naught, and we can say that this T naught would be equal to Ts plus, this part is becoming 0. Okay, this R is getting 0, so we can write Qg, by 6k into R0 square. So this is our maximum temperature, and this is the temperature distribution. Again, we can form a non-dimensionalized temperature distribution equation, but we are not going to do here. I think you will understand it, how you know the processes, how you can generate the dimensionless form of temperature, and I hope you will do it by yourself. Okay, so after understanding this, let us try to calculate the heat transfer rate at uh, R equal to R naught. Okay, so let us try to find out R equal to the heat transfer rate at R equal to R0. Okay, so it is quite understandable that this heat transfer is only because of the internal thermal energy generation that is taking place. So after the calculation of this heat transfer rate, we must find that this heat transfer is becoming exactly equal to the total thermal energy generation of uh, the total thermal energy generation. Okay, so what is our formula? This is our basic formula, K A dt dr, but this dt dr should be calculated at r equal to r naught or r0. Okay, so after doing the calculations, like putting r a area as 4 pi r0 square and getting the derivative as, the derivation will give us it will be simply giving us qg by 3k into r. Okay, so it will give us qg by 3k into r at r equal to r0. So this is our task. That means we can put this r as r0. So it will end our calculations. Very simple thing. We can put r equal to r0, right? So we'll find that, okay, I'm very sorry that there will be a minus sign here, so that this to minus, ultimately the effect would be positive. Okay, the derivation of this part would give you a minus qg by 3k into r. I had missed it in the earlier stage, but I think now you can understand what I'm trying to say. This k are the same terms, so they wouldn't be present also, and ultimately you are left with this formulation, 4 by 3 it will be, sorry, 4 by 3 pi r0 cube into qg. This is kind of a recapitulation class going on. I don't know if you're getting bored or not, but this is the same process we are following for all the three geometrical surfaces. But still, we must do it. You must do the calculations, um, so that you must get used to the calculation. That is my main point. Okay, so here, this is our basic understanding. This is your volume. This is the volume of the sphere. So Vs into the volumetric heat generation. This gives you the total heat transferred or the total thermal energy generation. Both of them are same. So please remember this equation. This is the general equation. This equation gives you the maximum temperature at the center. Please always remember, for sphere, for cylinder, the maximum temperature is found at the center. For plane walls, the maximum temperature is found along the mid plane. Okay, so please remember, these are very symmetric things. I think if you are able to draw the image, then you will remember by yourself. So after this understanding, let us take some problems so that uh, we can be confirm of ourselves that we have understood this whole concepts in a much better way. So let us start with the first problem. So let us just read out this problem. A 8 centimeter diameter orange, approximately spherical in shape, undergoes ripening process and generates 18,000 kilojoule per meter cube hour of energy. If external surface of the orange is at 6.5 degrees Celsius, find the temperature at the center of the orange. Also determine the heat flow from the outer surface of the orange. Take K equal to 0.8 kilojoule per meter hour degree. So you know the radius is 4 centimeter, that is 0.04 meter. The internal thermal energy generation is given as 18,000 kilojoule per meter cube hour, but we are used as the units of watt per meter cube. So better we convert this unit in watt per meter cube, and which gives us 5000 watt per meter cube. Okay, the external surface of the orange is at 6.5 degrees Celsius, that we have written here, and the thermal conductivity is given as 0.8 kilojoule per meter hour degree. Again, we would like to convert the units from kilojoule per meter hour degree into watt per meter degree, which we have done by converting this kilojoule into joules and this hours into seconds, so that joule by seconds becomes the watt. Okay, so after that, the question is to find the temperature at the center of the orange. So to find the temperature at the center of any sphere, we should abide by this formula, and after understanding that we have all the data available to calculate this, that means we have Ts as 6.5. So ultimately you will find that if you go on putting all the relevant data which is available to us in terms of if you put Qg as 5000 watt per meter cube, K as sorry, I had missed it, sorry, it will be 0.222 watt per meter degree. Sorry, I didn't do the calculations, or I haven't written it. So you will find that if you go on putting all the relevant data which is available from the left side here, you will find it would become, that means the temperature at the outer surface would become, I'm very sorry, the temperature at the center of the orange would become 12.5 degrees Celsius. You please do your calculations by your own, and you'll find that this would become 12.5 degrees Celsius. Now the question is the heat flow from the outer surface of the orange. What is the heat flow? Heat flow is nothing but the generation of thermal energy, right? So if we do this thing, Qg into volume of the orange, which is spherical in nature, so the volume of any sphere will be understood from this formula. This R0 is our radius here. This Qg is the volumetric heat generation, that means heat generations per unit volume. We just simply need to multiply this Qg with the volume, so that we have already told you that while discussing the one-dimensional steady state equation for spherical surfaces with thermal energy generation, the heat transfer is only because of this thermal energy generation. So the heat flow which is flowing from the outer surface, that is because of this internal energy generation or the thermal energy generation, that can be simply calculated from this formula. And you know R0 is 0.04, you know Qg is 5000, and ultimately you will find it would be it would be 1.34 joule per seconds. Okay, 1.34 joule per seconds, which can be also written as 4.82 kilojoule per hour. So it is dependent on you. You can choose anything of this. Both of them will be correct. So this is a problem. This was a very simple problem. Just you had to use the formulas. So it was nothing but the application of the formulas. Okay. So after doing this, let us take a little complex problem, but it will be easier. But let us see how it can be solved. So let us read out the problem. A solid sphere of 8 centimeter radius has an uniform heat generation of 4 into 10 to the 6 watt per meter cube. The outside surface is exposed to a fluid at 150 degrees Celsius with convective heat transfer coefficient of 750 watt per meter square degree. If K, that means the thermal conductivity of the material, is 30 watt per meter degree, determine the maximum temperature and its location. Temperature at 5 centimeter radius. So you know that for any spherical substance, for any spherical surface, the maximum temperature would always occur at the center point. Okay, so the maximum temperature is occurring at the center point of the spherical surface. So the location is understood, well understood. Now the question is, how can we calculate this maximum temperature? That should be calculated by this formula. So here this is the thing which is very much unknown to us. This is the external surface temperature. That means you need to calculate the surface temperature of the solid sphere. And how you can calculate it? This solid sphere is exposed to a fluid at 150 degrees Celsius. That means the heat which is being generated, the thermal energy which is being generated within the solid sphere, is getting exactly convected away to the fluid. That means heat generation, the total heat generation or the total thermal energy generation will be equal to the heat transferred by convection at steady state conditions. So the total heat generation, that will be very much easy to understand. Volumetric heat generation, Qg multiplied by volume. We have seen it. We have seen just a few moments, just some minutes ago, that the total heat generation is found by this formula, so which can be written as R0 cube, and this heat is being transferred via convection. So we can write 4 pi R0 square. I am directly writing the formula of area, mind it. And the heat transfer is taking place between the surface, that is Ts. Better I write Ts here, because we have used Ts, and the ambient temperature is 150. So I can just replace this Ta with 150. Okay, so I can replace this temperature by 150. Now the question is to find this Ts. Now after doing simple calculations, you will understand that this part will be removed from this equation. Similarly, this would be also removed. This can be also removed. So the equation remains like this: Qg into R0 by 3, Qg into R0 by 3 is equal to H into Ts minus 150. Okay, so after doing the calculations, you will find that this Ts would be, so I think you were able to understand how we can reach the solution, and you will find that this Ts would be 292.22 degrees Celsius. Okay, so very simple calculations. Ts will be equal to 292 point, okay, just let me write this once again, 292.22 degrees Celsius. So this is the surface temperature. Now the question is to find the maximum temperature. So how you can find it? You just put this value here and calculate the this function depending on this data available here. So you'll find, after putting all the relevant values, you will find that the maximum temperature which is occurring at the center of the sphere as 434, sorry, it will be not 424, it will be 434.45 degrees Celsius. Okay, so this calculation should be done by yourselves. I have already calculated it, so I'm just putting the data here. Okay, but the calculation should be done by yourself. So we have done with this, we have completed this problem, and now the question is to find the temperature at 5 centimeter radius. So if you remember the temperature distribution formula that which we had derived, T minus Ts as Qg by 6k R0 square into 1 minus R square by R0 square. If you remember this temperature distribution formula, then it becomes a problem of 2 minutes. Okay, you can just replace this R as 5 centimeter and you can get all the relevant data. You know Ts, you have already calculated Ts as 292.22, you know Qg, you know R0, you know R is nothing but 5 centimeter. So always remember to convert this centimeter into meters, and after you put all the data which is available here and this Ts has been calculated just now, you'll find that this temperature at 5 centimeter radius would be found as 378.99 degrees Celsius. So I'm not going into the calculations, I am just putting the final value, 378.9 degrees Celsius. So very simple problem because you have all the data available with you. So the heat transfer, so the conduction heat transfer with thermal energy generation for spherical surfaces, the numericals are very much easy. Okay, so after understanding this, so we would like to end our lecture here. And in the next lecture we will start discussing about the combined conduction and convection problems. That is, we'll be discussing how heat transfer can take place via the extended surfaces, or specifically, to be much more specific, we'll be discussing the concept of fins. So till then, goodbye and thank you very much.